Say that again?
Well, I keep looking it up because I realized...
Oh, you see, you guys are interested in this. I'll take a quiz on this, maybe.
There's even fossils that when they dug them up were...
Show-handedness?
Right.
Fossils of what? Of human remains or animal remains?
Like 12 little known facts about left-handers, but in there they had thrown that there were fossils to even show that they were right.
We gotta make a quiz on this. Yeah, because this has to be a quiz. It just has to be. It's too interesting not to do something. I already made your exam, so I can't put on your exam. But I want to make something about this now. This is fun, right? This is fun. What's the commonly accepted percentage of left-handers in the United States? Have they stated that? Is it like 1 in 7, 1 in 6? Lower than that, 1 in 10 maybe?
10%.
10%. 1 in 10. Okay. I can totally build a quiz around that.
Don't you have to then go to the, because in my mom's day and even in my day, any of the left-handers, like the nuns would stand over.
Oh yeah.
And
I'm recovering Catholic. I remember those.
Rulers, and if they were using their left hand, and
so then we can do maybe a pre-post. Maybe it did. Well, the demon thing, the religion thing. I mean, it's starting to sound religious.
So are you two left-handers that have learned to be right?
Mm-hmm. You guys ask such good questions. You really do. I mean, I love the fact that you're asking these. I have no good answers. Because it's all contextual, right? Yeah, I always feel like a fraud to some degree. Because what we do in this class is we learn tools, right? But I can't show you how to build a house with these tools. I can take your house plans and help you build a house later on when you're in your research fields. We're doing that right now with a couple of different people. But you ask great questions. And now you have the tools to approach that through the data. Rachel's already on it, thank you. And I'll go dig some more too for next week. You've totally given me guidance on how to make a binomial quiz for next week. Thank you. Namaste. So it's gonna be fun to look up this data and actually play with it a little bit. So it's good. It's good. It's damn good. Anyway, thank you. So here's something to make you nauseous.
Oh no.
This it's okay. It's okay though. So what this is nothing that you're going to have to memorize or know. But I want to share with you the importance of something like this. So this would be, if you were to take math 243, 244, 255, 246, 247, 248, 249, 250 up to about 296, if those classes existed. This is, from what I can tell, every named distribution that is currently used in statistics. So, you guys learned starting about 4 weeks ago the idea of a probability distribution. A probability distribution is a XP of X table where you list the values of the random variable combined with their probabilities. Say that again. A T-chart, exactly. Thank you. A T-chart. That's right. T-chart. These all have essentially T-charts, but as you just saw, some of them are specialized. In other words, they have special behaviors that you can use to your advantage. Like the binomial, for example. If you can show that a random variable is binomial, then you get certain freebies. So if you look up there, the binomial is right here. And tucked next to that binomial, you have the formulas that I mentioned over there, kind of tucked in there, tucked in right there. So what you have here is a table of all of the related distributions. You'll notice there's one over here called Bernoulli. Now, a Bernoulli is a very special binomial. A Bernoulli is essentially the coin flip 0-1 binomial. That's a subset of the binomial distribution. It's one special case of it. And if you look at the binomial, it then goes out to many different kinds of distributions. Now, what I've done with this chart is I've kind of highlighted a few of the distributions that I've used in research and in helping people bring, for example, data to court cases and things like that. The geometric distribution is a pretty fun one. It's like the binomial, except there's not a fixed number of trials. There's an independent probability at work. But whereas the binomial says, I'm going to have this many trials and analyze this many successes, the geometric says, how many trials do I have to run to observe this many successes? You see the slight difference there in the presentation? It's kind of like solving for a different variable in an equation. Now, it's a great function, but I don't like torturing 243 students with it because it's so specialized. If you ever need to use it in your lives, email me. We'll use it together. Here's another fun one, the Benford distribution. This one way down here. The Benford distribution, it was actually used relatively recently to show there was most likely voter fraud in the first Iraqi democratic election. which I found fascinating. They used Benford's law to say that, you know what? You might want to look into these districts in that Democratic election. It looks like the ballot boxes were rigged. The reason they were able to say that was when you have a sequential list of integers, think of your checkbook. Think of your checkbook. You know you have those check numbers in your checkbook? I don't know where this canceled check came from. I'm breaking my wall by putting it up here. But they have check numbers. 1, 2, 3, 4, 15, 16, 17, blah, blah, blah. Benford, a statistician, discovered that if you have a string of numbers like that, a certain percentage of them should be 1s. A certain percentage should be 2s. A certain percentage should be 3s. And think about why.
Yeah.
If you're counting, you know, you get into the hundreds, 123, 124, 125, there's a lot of 1s. There's a lot of 2s. There's not so many 5s within a reason until you get to the 500s, right? So if you analyze the entire string from 1 up to n, there's certain percentages of digits that should show up. If you don't see that over a certain realm, it means people may, not did, right, Gray, may have rigged the ballot boxes by using one number too many times, maybe not paying attention to that kind of stuff. But again, a very, very, very specific distribution, not one that I would make you guys do on an exam or anything. Fun, very cool. Exponential distribution models lifespans of electronic parts really well. So if you ever get into a field where you're looking at LED lights or server life or things like that, you might want to look at the exponential distribution. Again, it has neat little characteristics. The poisson is one of my favorites. First of all, it's a French word, which makes it fun to say. Poisson, huh? It means fish. I don't know why the hell that has to do with that. It means fish, right? I'm trying somebody's name. But it is able to model really, really well weird random events. You see how it's tied to the binomial? Is that me beeping? It could be the stopwatches. It's tied to the binomial. It's what happens when a binomial's probability gets really, really, really small. When it gets really, really, really small, it's oftentimes easier mathematically to use the Poisson function than the binomial function itself. It's got a neater equation. Now, again, I don't care about that. You don't care about that because we use technology.
Is that in my T3?
It would be, the Poisson. Oh, it's not in your Disfill program. I didn't make that an option, but there is a Poisson PDF. If you go into your distributions, it's in there.
Oh, okay.
And if everyone know how to use it, I had to use that in a court case once. Zelda Ziegler, you guys know Zelda? Teaches chemistry, I think. She had a former student who was being prosecuted. He was a member of ELF, the Earth Liberation Front. And those guys they're kind of scary. They're rabid environmentalists, and they do things like set fires to places that they think have infringed upon wilderness areas. And this kid was allegedly tied to 8 fires. Allegedly. I have no idea how this case actually ended up going in court. No, I do. He was tied with 8 ELF fires. And the prosecuting attorney said, well, this is a wanton disregard for human life by doing this. And Zelda was like, I don't think so. I don't think that that's what he was after. He wasn't after killing people. He was after getting rid of structures. Like they would set the fires in the middle of the night when there was nobody there to burn them down to let Earth reclaim the structure. Now, I'm not saying that's a good idea, but I'm saying that their accusation of him as being wanton disregard for human life was maybe unbiased. So what I did was, to support her hypothesis, she couldn't do it mathematically. I said, what's the chance that if he sets 8 fires with no regard for human life, that there were 0 deaths in those 8 fires? And as it turns out, statistically, you can look at intentional arsons in America over a time period, and there's usually an average number of deaths per those fires. I forget what it is now. I can dig it up for you. It's in my archives. But there's an average number of deaths per fire. So let's just say it's 3, for lack of a better term. If the average number of deaths per fire is 3, how likely is it that this kid had 0 deaths over 8 fires? Right? Now that's not quite binomial, is it? Because there's no probability in there. There's an average in there, right? There's an average, and that becomes the parameter of the distribution. So I used the Poisson distribution and took it to court. He did get off. I mean, he got lesser charges. He didn't get charged with attempted murder. He was charged with simply trespassing and setting fires, arson, which he was guilty of. He admitted to that. But they dropped the whole charge of attempted murder, which I thought was brilliant. Well, because of mathematics, which is kind of fun, Yeah. So anyway, Poisson distribution, it also models things like insurance companies use that one to figure out how many times people are going to fall down in the shower and claim insurance based on shower falls. It's a weird, wacky probability. If it doesn't happen very often, what it does, you get these big claims that come in for it. So, traffic patterns, it models traffic patterns beautifully. I wish the city of Bend would use it more on certain lights.
Especially on snowy days.
Yes, exactly. The Powerball, actually, I would love to see them use it more when they model the snow versus the non-snow. Man, right now the traffic is so weird in town And again, being on a bike, it's much easier. I can just ride alongside of it. But coming down, I was coming from Max's swim lesson last night, down 14th. Yes, 14th is the one with the flaming chicken roundabout, right? That's 14th. Century Drive into 14th. Traffic was backed up from Greenwood through the chicken roundabout, back to almost, what's that, Cabin 22 now? Like, seriously? Like, why? And then it's because of the snow. Like, why because of the snow, though? And then I start realizing, oh, it's probably due to the side streets and all this stuff. So, anyway, it would do them well to use a Poisson model and look at the traffic. Powerball, hypergeometric, my last favorite, then we'll stop talking about this because this is kind of terrifying to look at, I know. The hypergeometric is the binomial, and this goes to you, Linda. It's the binomial when you can't prove independence. So earlier you said, oh, it becomes dependent, not independent. If you can check off probability, if you can check off fixed number of trials, but you can't check off the independent part, you got to use this guy. Now notice, he's tied to the binomial. Gesundheit. But the problem is, it has to satisfy these conditions, and those are the independence conditions and symbols. So if you can satisfy the independence conditions, it becomes binomial. If you can't, you have to go with hypergeometric. So the reason they use it for things like Powerball is, Powerball, you've got, what, 59 balls that you draw 5 from, right? You're drawing 5 balls without replacement from 59. You can't treat those as independent. You're taking too large a chunk of the 59. So it's like Max going into the store and buying 4 birds, and there's only 40 birds in the store. That's a different situation than when he pulls 4 birds out of 1,000 birds in the store, isn't it?
Yeah.
You see the difference there? So if you can't check off the independence assumptions, you gotta use the hypergeometric. This slide is totally not intended to be like, oh my god, I have to memorize all this crap, because you don't. I love it because some of this stuff, I don't know what the hell it does. I've never heard of half of these distributions. I myself personally have invented one that's not on here. You'll see it in 244 if you take 244 with me. So God knows how many are actually out there. This is one of my favorites. This is the one you can analyze the M&M candy color distribution with. Not to mention, you can analyze genetics with and other things. I mean, they're wonderful uses. But, oh, go ahead, Sam, what are you going to say?
Well, on the geometric, I was wondering, now would they use that in science? I know
they could.
They just were doing the virus for the starfish.
Oh, I haven't heard about that one. And I wouldn't know how the geometric would tie to it.
On the West Coast, so like...
Oh, virus spread in starfish that are killing them off or something?
Yeah.
It could very well be number of infections until past a point of no return.
Until they found the virus.
That doesn't surprise me at all. It could be used. I can see how you could use that one there. You could also do it binomially by saying we're going to sample 100 starfish and check for the virus. Yeah. So it depends on what you're trying to model. Are you modeling the number of virus interactions until infection, or are you just trying to estimate what percentage you're being infected?
Right.
Sometimes it's which question you're asked tells you which distribution to use too.
Which distribution to use.
Right. Right. Like, for example, if you want to compare the one species of starfish to the other, you use the T distribution. But if you wanted to compare one starfish here to a starfish here to a third starfish, you have to jump down to the F distribution. I mean, there's all kinds of, it's all what are you measuring, right? And then 244, we increased the number of distributions in 244 a little bit. We never get close to this. This is insanity, and I love it. But that's not what I came here to tell you today. I came here to tell you that there are only 2 I care about in 243, and you know one of them already. The binomial is the one that we just spent a week and a half, almost 2 weeks, living in. We'll have some quizzes next week on it, and I love it. The one I want to start talking about today is this guy, the normal distribution. It's kind of a weird name, normal, the normal distribution. I don't know why they call it. Honestly, I have no idea why they call it that. But you've been calling it something else ever since about week 3. And you'll see momentarily what you were calling it. You haven't been calling it the normal distribution. Every once in a while, I'll let it sneak out in our discussions. But you've been calling it something since week 3. So I've been kind of prepping you for these last 2 weeks. I like the last 2 weeks to be kind of a slide into home plate. And by prepping you for this early on, I can tie it all together much, much easier and hopefully make you guys have a less mentally taxing last 2 weeks of class. So what I'm going to do is I'm going to show you why you recognize this new distribution by looking at an old distribution, the binomial. So we've been talking about these ones that have a probability of 1/2 for about an hour now with Max and his Crocs. So flipping a coin is a good example of that. Checking the color of a card that you deal to yourself. That's half and half, red and black. Arguably the gender is half-half. I mean, 50%. Things guessing, Max guessing on his Crocs. So check this out. You'll have this PowerPoint set up for you guys. You don't have to worry about drawing this stuff now. That's what the distribution, I did it in Excel and not dist fill and distro. I hope you guys don't mind. It's a little bit prettier in Excel.
It's very nice and.
It's got the color in there. And,
Yeah.
oh, FYI, if you ever need to do this in Excel, the quiz for Standard Paneling for this week has a link with a quick video where I show you how to get a distribution for a binomial and a graph for it in there. So if you ever need it, it's there, or you can always just ask me and I can help you with it too. So anyway, this is 3 trials, 3 coins flipped. Think of it that way, 3 coins flipped. What's the chance of getting no heads? About 12.5. What's the chance of getting 3 heads? The same, because 3 heads and 3 tails is just as likely as each other. What's the chance of getting 1 head, 2 tails, or 2 heads, 1 tail? 37.5%. This is exactly the same distribution you guys would have gotten if you run dist fill and dist draw in your TI. Linda, go.
Do all these probability percentages, they have to equal 100?
Yes. So 12.5 plus 37.5 is 50%, plus 50 more is 100. Thank you. What's the average number of heads we should get in 3 flips? On average, how many heads should we get? Don't overthink this. Half. So therefore 1.5. Thank you. Yes, don't overthink it. Don't overthink it. You got 3 trials, and you know it's a half probability. Half the trials should be heads, half should be tails. Sure, it averages to 1.5, and you can't flip a half a head. But that doesn't mean you can't average half a head flip, right? Thank you, Rich. Absolutely good. Okay, let's keep going. That's if you flipped 5 coins. Going back to Linda's awesome observation, the chance of getting no heads looks to be about 3%. 1 head and 1 head and 4 tails looks to be maybe 16%. 2 heads and 3 tails looks to be about 32%. That adds up to about 50%, doesn't it? The other 50 is on the other side. Average, on average, how many heads should we get? 2.5, 2.5, half the time. Good, 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 good. There's Max and his Crocs. There's Max and his Crocs, which is the same as flipping a coin. Remember how I put it to you? His head is flipping a coin to decide which shoe goes on which foot? Same thing. Should have averaged 5. He ended up down here with that little tiny bump. Right, little tiny bump. It means it's an outlier, most likely, or most unlikely, I should say. Cool. What if we watched him? This was Linda's request more than 10 times. There's 25, average 12.5. There's 50, average 25. There's 100, average 50. Now notice what's happening as we're increasing the sample size. What's happening down on the bottom? That bottom axis. What's happening? Go ahead.
We're collected. I'm trying to think of the term.
No, you're use it. Good. Say that again. Good. What's shrinking? I love it, Kendra. I love it.
I don't know how to explain it.
It's okay. You guys, you're doing this with your hands, which is perfect.
Yeah.
What's happening is the tails, obviously the bottom's getting wider. The first graph I showed you only went from 0 to 3, so it was over here. Then it went from 0 to 5, then 0 to 10, then 0 to 25, then 0 to 50, and now it's 0 to 100. So clearly, the standard deviation is getting very, very wide because we have more and more options to deal with, right? But what's shrinking is the area that's in here. These bars are getting smaller to fit better. And you're getting, what does this look like?
A bell shape.
It's a bell shape. Guess what a bell shape's formal name is in statistics? It rhymes with formal. The normal distribution. A normal distribution is another fancy statistical term for a bell curve. I mean, that's what they call it in statistics. They call it a normal distribution. Why? Hell if I know. Why do they call it right-handed, right-handed? I don't know. We just do. So you get, now even the first one arguably kind of looked like a bell curve. It's rough, it's squarish. But as you let that sample size get larger and larger and larger, it starts looking more and more like a bell curve. That's why in that original distribution there were arrows between the binomial and the normal. Because as you let the sample size go up, they start looking almost identical to each other because those little bars keep shrinking down. Now that's a consequence of how I graphed it too. I could also make those bars as wide as the other ones. But that still wouldn't change the shape. It would still curve up and rock. It's got a cool little inflection. It goes up and then it inflects over and then it inflects again right here. Very cool. We'll get back into that, if not today, on Tuesday. But you're starting to see also, since it's a bell curve, why do we get so excited when we see bell curves? You can make predictions around them. You know the average is 50, and you know, as Sandra told us earlier, you can go then standard deviations out, can't you? We can start doing standard deviations out. Good. So, what I start looking for in my data, and I was doing this today with my Math 244 class, we clicked on a bunch of data in class today, and I kept graphing their data, and I started looking at it. Here's some examples, not of 244 data, but data I've pulled from research. Oops. There are 118 through 24-year-old American women's heights. Notice a pattern in the data. It's not quite as pretty as the binomial curve, is it? But do you see the bell curve in there? It's not perfect. It's not perfect. I don't think anybody's going to look at that and go, it's highly skewed. I mean, you could say that, Johnny left. He might. That's okay. He might. He might say, I think it's skewed. Of course it's skewed. The question is it so skewed that you won't call it a bell curve? I don't think so. I can see it. Sure, that bar's a little low, maybe that bar's a little high, but you can kind of see the bell in there. I think this is one of the same distributions we looked at a few weeks ago. LDL readings. You see it in there? A little bell curve, a little bell curve, yeah, a little bit, tiny. 100 random IQs.
Yeah.
Uh-huh. Now, what is IQ? Intelligence quotient. How do you get one of those? You take a test. What does the test measure? The size of your mental age. Technically speaking, the size of your mental age. What is an intelligence quotient the quotient of? That's exactly right. It's the quotient of your mental intelligence age divided by your chronological age. And then they turn it into a percentage. That's why the average, and you can tell what the average is by this curve, can't you? The average IQ is 100. 95 to 105, which right in the middle is 100. Because that means your head is as old as your body, so to speak. I'm being very crude and crass. Your mental age is the same as your physical age. So if I'm 41, and I tested an IQ and I came out as a 41-year-old mind, I'd have an IQ of 100. I'm average IQ, perfectly average IQ, right? I'm perfectly average because 41 divided by 41 is 1 times 100 is 100. If I give my then 2-year-old son an IQ test, and he tests as a 4-year-old, he's got an IQ of 200. Because 4 divided by 2 is 2, times 100 is 200. I would never give a 2-year-old kid, or any child for that matter, an IQ test because I don't care about it, because I don't agree with what intelligence is or is defined as. But that's how it's defined, just so you know, that's how intelligence is defined. So when you take one of those tests, that's what they're actually doing in the computation. Interesting. Interesting, huh? Here's a few other things that are bell curved. Take a look at some of this. Yeah, thick as a tree bark. Isn't that fun? Next time you're walking down Chiplin Park, just wander around and look and think about that. But don't ruin your nature experience by thinking about statistics. Just wash your reading.
So times of eye contact with schizophrenic patients. Yeah.
Times of eye contact. Is there a left-handed up there?
No.
Oh, damn, I thought I maybe I stuck one of those in. Times of eye contact with schizophrenic patients. Sizes of wine bottle corks cut by a machine. The amount of soda in a 12-ounce bottle is bell-shaped. It's not always 12 ounces. It averages closer to 12.1 ounces because we live in America. And because if you get 11.9 ounces, you'll sue the company and then they'll have to pay out millions of dollars to you. But there is an average, and there's variance around that average, and it turns out the variance is bell-shaped, which is pretty slick. Ball bearings, actual volume of 15-gallon gas tank in a car. I used to do this one in class, number of chips in Chips Ahoy chocolate chip cookies. I used to do that in my statistics class, but it got too messy, and it pissed the students off because they couldn't eat them then. So then I had to buy 2 bags, one they could eat, one they could count, and it just, the janitors get upset with me. So
Yeah.
hip breadth. This is one of my favorites. I might make this one a quiz for you guys in the last week of the class. It helps you design, say for example, airplane seats. You know, how big should an airplane seat be? Well, it should be big enough so that you don't physically damage a person sitting in it. But you have to know what big enough is. So what would big enough be, right? What would big enough be? So there's all kinds of heights of people. I remember going to Bishop, California years ago for a bouldering trip, and staying at a hotel because we had Max. He was like 3, and we got tired of staying in tents with him because he would wake up in the night screaming. So we got a hotel room, splurged, and I walked in to take a shower, and the shower head was right here. And I'm like, I wonder how many people this is inconveniencing. That's the first thing I think of. See, I'm ruined. I'm ruined. I don't go, I want to call the friggin' management, give me another room with a damn shower head higher. I think, I wonder if we've got like 50% of people being inconvenienced by this. You know, it became a quiz, of course. So, anyway. Lots of things are bell-shaped, which is fun. And it gets even better than that. It gets even better. Oh, this happened yesterday, too. I might have just froze PowerPoint. Hang on. I did. there's a video linked to the next page, and oh, wait, maybe I didn't. Yes, I did.
It's thinking.
It's thinking. You shouldn't have to think so damn hard. Yeah, same thing happened yesterday. Patience with me, friends, I'm sorry. Go ahead and restart, that's totally fine. We'll go straight to that slide. I wonder why that's happening now. Oh, because they upgraded, because they changed it, they have a new version of PowerPoint. So of course the old version won't work right. That makes perfect sense. Yes, I want to save that one, shut up. I want to go to, oh, this is the wrong one. I don't want binomial, no, it's over here. There we go. I want, there we go. Let's see if I get it to work. Fingers crossed. Hopefully it becomes a picture. Maybe. Yes! You ever been to OMSI? This is an OMSI. You can check this out. Max will explain the whole thing too if you don't understand it. Yes, this is a Corla. It's wonderful. And this is a display that's always there. It's not one of those ones that changes in and out. It's actually always there. Come on, load. You loaded yesterday.
That's right, sweetie. And then start again.
Ignore my Kermit the Frog voice. So what's happening is they're taking little tiny white balls up to the very top up there and dropping them in. There's a series of pegs in the path, and the balls are coming down and bouncing off the pegs, and they're collecting them down here. It looks like the game Plinko, Price is Right. It's exactly the same principle.
Oh, yeah?
We just went back 2 weeks ago and he did almost the exact same thing, so you can understand what he's saying now. Almost exactly the same thing, though. So you see what's happening? Yes, we're getting a hump in the middle of it. Why? Why is it harder to get away from the center? Eric, I love that. Why is it harder for the balls to get away from the center? Now, there's an easy answer, right? The easy answer is they're being dropped in the middle. But why is it so hard for the balls to end up over here? So what did Linda go? They have to make so many right or left turns. If you think about it, if you think about it, when a ball hits the peg, what's the chance it goes left? Probably 50-50, right? There's probably all kinds of little tiny butterfly effect things that are happening. Is that what you were going to say, Kevin, before?
Well, no, I was just going to say it has to hit a bunch of them.
Exactly. It's good. There's a whole bunch of butterfly effects, like the balls rotating or what, but those are all so random. It's going to even, I think, over time. Look what's happening. Look at that. So what happens essentially is every time a ball hits a peg, half the time it goes left, half the time it goes right. But that's an average of half and half. It does not go left, right, left, right, left, right, left, right, left, right. If that happened, you'd think something was wrong with the machine, right? So what happens is, most of the time, for every left there is a right, it might go left, 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 right, right, left, right, right, left, left, right. But the majority of the time, the lefts and the rights are canceling, and you're going to go close to the middle. You get the outliers where you go left, 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 left. What I like to think about is, and they don't have that in the machine. The machine is only about 6 feet wide. I would love for it to be infinitely wide on both sides. Right, of course, because of me. But because chances are, some of those ones in those last bins would have gone further if they were allowed to keep making their turns, right? It would also be infinitely high. So you can see what I did to build this, obviously. But that would be freaking rad, wouldn't it? Like an entire wall of OMSI devoted to just that? Oh, God.
It'd be really cool.
That'd be really freaking cool. I'm just thinking about that now. I'm glad I'm recording this. I'll go back and look at it later. And it's taking pictures of me right now with my finger on my nose. It'd be loud as hell, but you could also then make them out of like some kind of metal that resonates and make music maybe. Have them all different tones.
Yeah.
I like this too. I wish I had more time to do it. Anyway, but the point being, and if you go back in the PowerPoint, which I'm not going to do because I don't want to screw up the PowerPoint again. It turns out this has a name. I had a theory years ago that says a lot of those things on the previous slide that were bell-shaped, and even the IQ scores and the LDL levels and the heights, all those things have lots of little tiny factors that influence them. Lots of little tiny left and right turns. So for example, you're making a ball bearing. The machine is making a ball bearing, right? You've got this raw material that goes into a ball bearing, stainless steel, right? Stainless steel goes into the ball bearing. There's all kinds of little fluctuations in the recipe for stainless steel that go into that ball bearing. Then there's the machining of the ball bearing, which has little tiny bits of variance too. So by the time you go from raw material to the final product of a ball bearing, lots and lots of little machining and variance items have been encountered. So all those little tiny back and forths tend to recorrect over time. Like if something's a little too heavy here, it'll be corrected a little too light here, on average. Sometimes not, sometimes yes. So I think if you look at like how big a gas tank is, how much IQ someone has, think of all the factors that go into whatever intelligence is, all the factors, let's give it a different name. Let's call it intelligence, let's call it knowledge, right? How many factors go into acquiring knowledge? Lots, right? Lots. It seems like when lots and lots and lots of things contribute to the end result of a product, those things tend to be bell-shaped. For some reason, because most of them correct back to some central average. But then the almost predictable tailings that happen, there's a mathematical reason for that inflection that happens. But as far as understanding why so many things are bell-shaped, I think it's just because of little natural variations. And apparently I'm not alone. They call it the fuzzy central limit theorem. Because nobody can prove it. Nobody can prove it, but it seems like there's an underlying pattern in egg incubation times is one of them, right? Egg incubation times for chickens. How many different environmental, biological factors go into that, right?
Quite a few.
Quite a few, exactly, quite a few. But somehow, when they all average out, they end up falling in kind of a mound, a bell shape, which is pretty cool, I think. Now, it's not just me that kind of thinks it's everywhere. The German people for a while, I love this by the way, the German people for a while didn't use the euro, they used the mark system. This was a 10 mark or a $10 bill for them. Now we put people like presidents, useless people on our bill. What do they put on their money back in the day? Mathematicians. That's Carl Friedrich Gauss. Let me introduce you to Carl Friedrich Gauss. Largely considered one of the greatest mathematicians that ever lived. He was wonderful. He was also kind of a weird mathematician. When he was very, very young, I think he was 5 or 6 years of age, him and his class were being rambunctious in school. And the teacher got pissed at him and said, okay, get your slates. This is like 1700, I think he was around. Yeah, 1770 to 1855. Grab your slates. I'm pissed off at you. Add up the numbers 1 through 100, the integers from 1 through 100, and then you can leave. And you've heard the story? It's a wonderful story. And it's true. It's the best part. And Gauss wrote the answer down. Within seconds, put the slate down, face down on the teacher's desk, and walked out. And the teacher was like, pain in the ass. And then one by one, the other kids did their work, put the slate on the desk, and this guy's got this big stack of slates with Gauss's on the bottom. And he's like, all right, I better get around to taking a look at these things. So he grabs the first kids and looks at it, and the kid screwed up. So kid screwed up. He gets down to Gauss's. All the kids did it wrong. He gets down to Gauss's. And he's like, Carl. He pops it over. 5,050. With no work. 5,050, which is the correct sum of 1 plus 2 plus 3 plus 4 plus up to. So the guy starts thinking, he's like, what the hell? How did he do 5,000? So the next day, Carl comes back in. How did you do this? And he goes, well, it was simple. Teacher, how was it simple? Nobody else got it right. They spent 8 times longer than you. He's like, well, I knew I had to go 1 plus 2 plus 3. This is all in German, remember. I can't speak this German that well. 1 plus 2 plus 3 plus 4 plus 5 up to 100, right? He's like, yeah. So the teacher goes, yeah. So you went 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. And Carl's like, no, that's dumb. He goes, you go 1 plus 100 is 101. Then 2 plus 99 is 101. And 3 plus 98 is 101. And 4 plus 97 is 101. The teacher goes, oh my God. And then Carl goes, and there's 50 pairs of those. 50 times 101 is 5,050. Piece of cake. And there was a turning point in mathematics right there, because the teacher was like, okay, you're 6. Let's get you out of first grade. And let's get you into like the university. And thank God he did, because then Carl Friedrich Gauss went on to give us some of the most amazing mathematical results like ever, like in mathematical history. Archimedes, Gauss, and Newton are considered to be the three biggies as far as mathematical results. So much of what we do in this class is based on him. Did you notice what's on the bill? Yeah, I mean, it's amazing. We put presidents and Knights Templar symbols on our money, and they put like math on theirs, which I think is great. Here's that equation I was telling you about. It's in there too. We won't use the equation because the problem with it is, I love you. I think the equation's great. I think it's fantastic. As it turns out, Gauss didn't invent the equation or even discover it. He just refined it. This guy, Abraham de Moivre, actually discovered the bell curve, and he got his own money. He got a little coin. There he is, Abraham de Moivre. But as it turns out, in order to use the equation to do what we need to do, you have to do something called a Riemann sum, which is an idea in calculus. You guys have taken the area of a rectangle, I'm assuming. You've done length times width there, rectangle?
Yeah.
Okay, we'll use that next time and I'll show you how calculus works a little bit. I can't do it in 9 minutes. I don't want to do it in 9 minutes. So next time, Tuesday, we'll sit down and we'll see how that curve relates to the binomial distribution you already know. It does and it doesn't. And the fact that it doesn't is good because it gives us a tool to use when we can't use the binomial. Because sometimes you can't use the binomial. Sometimes you can't, or sometimes you shouldn't use the binomial.
Right.
And there's a very good reason for that, many good reasons, but I don't think, like I said, I don't think 8 minutes is enough time to get into it. So we'll kick you out of here for today. Okay?
Okay.
Stay safe, stay warm, even though it's getting warm. So stay safe.
Stay safe.
Stay safe. And maybe dry. I think it's supposed to start raining tomorrow, I believe.
Today?
Yes. Today.
I heard today.
Oh, today.
And then
60% chance.
And then snow again?